Okay, so I want to really talk about this first law again. You can write it here: delta KE plus delta PE plus delta U is equal to Q minus W. Now I didn't do summations. I'm not saying there's only one source of heat. There's only one type of work. We could write this as 1/2 mass times V2 minus V1 plus mg times Z2 minus Z1 plus m times U2 minus U1 is equal to, some students like to do this. They like to say, well, this is equal to Q in minus Q out minus work out minus work in. They like to put this in here. And when they do this, and I'm perfectly fine with this, it shows you the sign convention that Q in is positive and work out is positive. Heat in is positive, work out is positive. What I always worry about is sometimes students forget, does this negative sign, what does it mean? What does it mean? And so that's where if you're doing it this way, I want to put absolute values on here so you can put the magnitudes. You can put the magnitudes of what's happening here. I'm giving this to you for you to use, but I would prefer that you would just do the summation here. And just say, okay, what's coming in? It's positive. What's going out? Negative. For work, what's going in? Negative. What's coming out? Positive. And just add all of those things up. That's what I would prefer for you to do. Okay? Sign convention again. Sometimes it's easier for me to draw a system here. So here's my system, and I am going to be drawing a boundary here, and I'm going to say here, coming in here, Q in, this is going to be, and this is going to be work in, here, Q out, work out. Okay? I want you to sit there and say, what's my sign for each of those things? Okay, I'm going to pause the video. Write them in right now. What's the sign? Okay, work in is positive. Heat in is positive. Work out, positive. Q out, negative. Work in, negative. You need to know these things. And note, because these heat and because work are crossing the boundary, it's still a closed system because mass has not crossed that boundary. Okay, mass has not crossed that boundary. This is important. Now, the main thing about thermodynamics is, and where this class can really get to you, is you have to read a problem statement and understand a problem statement and be able to decode that problem statement and then to put it into this equation. This equation algebraically is no big deal. You can deal with it. You've dealt with these things in high school, equations like this. Just adding some things up, subtracting some things, putting them together. But where thermodynamics really is won or lost is how you take that problem statement and read through it with your secret decoder ring and figure out what the heck it's trying to tell you. Okay, so that's what we're going to try to learn here. And that's why I am that's why I hate things like Chegg. Because if you don't struggle with that decoding of trying to figure out what the problem statement is, figures out what it's trying to say, you can really struggle in this class. You can look at what Chegg's saying and say, oh, that's simple. I understand where they went. But unless you can figure through and struggle through that, how did they develop that equation? How did they develop the solution? That's the real key that we're trying to learn here. Okay? Now, the first thing I want to tell you about that when we're talking about that is that the problem statement will tell you if there's no heat transfer. If no heat transfer, if a statement doesn't have heat transfer, they're going to say things like this. They're going to say it's insulated. Okay, that makes sense to you. You've dealt with insulated jugs before, insulated, your Yeti coolers. Insulated, we're saying there's no heat transfer. We're idealizing it as there's no heat transfer. Of course, there's going to be some heat transfer sometime, okay? But it may be very, very, very slow. And how I'm going to draw that system is I'm going to say, here's my system, and I'm often going to put like a crosshatch. I don't know if you can see this. A crosshatch? No, you can't see that. I'm going to put a crosshatch around the edges of it. This is going to be, I put a little, not really crosshatch, but dashed on the side of it. That's going to indicate that I have an insulated system here. So if you see that, that's my insulation. I also might say it's a poor thermal conductor. Okay, if the system's a poor thermal conductor, it's not going to conduct heat very well. Okay, a poor thermal conductor is another way of saying Q, heat, is equal to 0. That's what I'm trying to say here. And the last one is probably the word that is probably most often used, and it's the word adiabatic. So this is your vocabulary word for today. Adiabatic. Adiabatic. When they say an adiabatic system or whatever, and sometimes we're going to have to assume that a system is adiabatic. We're going to say, you know what? I haven't been given any information that tells me otherwise, so I'm going to assume or model the system as adiabatic. And that's where that model, assume part of your homework assignment is very important to me. You're saying, okay, I'm going to model this as adiabatic. Right now, we're going to give you lots of hints in your problem statement, but those things are going to change as we get going in this class. This is the point in time where I'm going to bring up to you this thing. This is a koozie that was given to me when I first started teaching at K-State. Koozie, you know, you put it around your cold beverage. It's supposed to keep your beverage cool, okay? And they put on this endothermic beverage capsule, okay? Endothermic beverage capsule. And when I saw this, I think I paid $10 for this. And you can see I have little yellow sticky notes because I've blocked off the names of the organization that was selling this. Endothermic beverage capsule. Okay, think about in chemistry. When they said exothermic reaction, what did that mean? Exothermic meant that the system was going to react and give off heat. Okay, what did endothermic mean? Endothermic means it was going to absorb heat from the surroundings. I don't know if I want my koozie to be endothermic. Okay, endothermic. That means it's bringing in heat from the surroundings. I don't want that. This is technology brought to you by your K-State engineers. I told them to take all of these and burn them in an exothermic reaction and get rid of all of them. And they said, they debated with me for a while, and then they realized, oh, this was wrong. And then 4 years later, I'm at an event, and there's the same organization, and they obviously didn't burn these, and they have them kept in a container, some box somewhere in the recesses of a storage unit, and they thought, oh, we need to sell these, and they started selling them again, and I went crazy. I said, just destroy these things. This should say adiabatic beverage capsule. Okay, that's my soapbox moment. I say it every semester. Don't be like this organization. Don't be like this organization. Okay, last thing we want to say about this in this section is this idea or this experiment that Joule did. Okay, Joule took a container, okay, and he insulated this container, so he made it adiabatic. And then he wanted to measure the properties of the let's say it's water here. Let's put water inside this container. There's water inside this container, and he put a thermometer in here to measure the property of temperature. And what he wanted to do was he wanted to say, I'm going to start here at state 1, and I'm going to move here to state 2. Let's just say let's do Celsius today. 20 degrees Celsius, and he wanted to move it to 30 degrees Celsius. And he wanted to see how we could get from that, in this closed system, how could we get from state 1 to state 2? So he added mechanical work. Okay, so let's go work adiabatic 1. Mechanical work he added there. Maybe what he did was he put a shaft in there, he put a mixer in there and just mixed it like crazy for a while, and after a while, he noticed the temperature rise to 30 degrees. And then he measured how much work was put into the system. And maybe he put some chemical work in. Okay, maybe he did some sort of chemical reaction to put in to change the system here. And this is work adiabatic 2. Okay. What he did was he found many different ways to go from state 1 to state 2. And you know what he found? That no matter how he got from state 1 to state 2, the same amount of work had to be put into the system. And that was pivotally important. Because if it took 30 joules of mechanical work, it would also take 30 joules of chemical work. That's very important. That's good for us. Could you imagine how the world would be like if we had to say, okay, it took 30 joules of mechanical work, but it took 25 joules of chemical work? That's just would make life so complicated. And that's why we name energy, we name it the joule because of this. And it makes our situation with our first law much easier now, because now we can say delta KE plus delta PE plus delta U is equal to Q minus W. And if we need to go from one state to another, we can see, as things catch up here, we can see that we can transfer energy in a number of ways over here. We can transfer energy by heat and by work, but we have to total up the right amount of transfer. The right amount of transfer. If it needs 30 joules to change my state, I can do 15 joules of work and 15 joules of heat. I can do 10 and 20, whatever may be, but these two transfers can add up. That's the amounts needed to change that state. And so that's a very important, very simple, maybe very obvious experiment, but a very important experiment when it came to thermodynamics. Okay, we'll pause there, and we have one more segment to talk to you about when we're talking about heat.